Hi, I'm Matt, and in this video we're going to do some additional practice with limits. So if you've watched my previous videos, I've gone through different types of limit questions, going type by type. This video is just a few extra questions I wanted to go through, and it also puts all the different types of limits together when you don't quite know which one or which method you're going to have to use. So for our first example, we're given the piecewise function that f of x is 3 minus x for x is less than 2, and then x minus 1 squared when x is greater than or equal to 2, and we're looking for the limit as x approaches 2. So, since this is a piecewise function, while we can plug x equals 2 into both of these expressions, I would suggest drawing a graph, because piecewise functions can have some weird behavior, especially at the points where the two functions, or the two pieces I should say, might not connect, in this case which is x equals 2. Therefore, it's always the safest bet with a piecewise function to draw the graph when determining the limit. So we're going to want to do our best to sketch the function here. So the first thing I'm going to do is draw our axes, and then I'm going to mark this point here as x equals 2. For the piece 3 minus x when x is less than 2, that's going to be a straight line with a y-intercept of 3 and a negative slope. And it's going to have a value of 1 at x equals 2. And that's because when we plug in 2 to here, we get 3 minus 2, which is 1. Lastly, note that's an open circle because its x is less than 2, and it's not less than or equal to. So here we have our left side. And now for our right side of the piecewise function, we have x minus 1 squared, and that's going to be a parabola. When we plug in 2 for x, we get 2 minus 1, which is 1 squared, which is just 1. So that allows us to close our initially open circle, and we see that we have a piece of a parabola. So this graph is sufficient for us to determine the limit, but for clarity, I've plotted the function in Mathematica here, and you can see it looks pretty similar to our sketch. So now we want to determine the limit. And since we have a graph, we're going to determine the limit by looking in the region around x equals 2. So looking from the left down this side, we see that we're approaching 1. Similarly, looking down the curved side of the parabola, what we find is that we're also trending towards f of x is equal to 1. Since the limit from the left and the limit from the right is both 1, we can say that the limit as x approaches 2 of f of x is equal to 1. And that would be our final answer. For the next example, we want to find the limit as x approaches infinity of the cube root of 3x to the 7th minus 4x to the 5th divided by 2x to the 7th minus 1. So as this is a limit as we go towards infinity, what we're going to want to do is follow the steps I've outlined in a previous video. And the first of those is if it's not a fraction, to make it a fraction by dividing it by x to the 0th. We don't need to do that here since we already have a fraction inside the radical. The only thing I'm going to do is I'm going to separate the numerator and the denominator into separate radicals, as shown here. And the reason we do this is now we already see it's a fraction and we could use the standard set of rules. Next, we're going to want to look at the numerator and the denominator, and we're going to want to get rid of everything except our highest exponent term. So in the numerator, the highest exponent is the 3x to the 7th, since x to the 7th has a higher exponent than x to the 5th. Similarly, in the denominator, we have 2x to the 7th and then 1x to the 0. 7 is greater than 0, so we're only going to keep the 2x to the 7th piece. So we can now rewrite this simplified as the cube root of 3x to the 7th divided by the cube root of 2x to the 7th. Next, we're going to take out our coefficients. So we're going to get the cube root of 3 times the cube root of x to the 7th. And then that's going to be divided by the cube root of 2 times the cube root of x to the 7th. And now for one final simplification, I'm going to rewrite this as the cube root of 3 times x to the 7/3 power divided by the cube root of 2 times x to the 7/3 power. So now, written this way, it's clear to see that in the numerator and the denominator, the exponents are both 7/3. Therefore, since they have the same exponent, we know that our limit as we go towards positive infinity must be either plus the cube root of 3/2 or the negative cube root of 3/2. Since when our exponents are equal, we just look at the ratio of coefficients. To determine the signs now, we now need to do a sign analysis of the numerator and the denominator. So in the numerator, we have a positive coefficient. Similarly, in the denominator, we also have a positive coefficient. So now all that we have to do is look at x to the 7/3 and figure out if that would be positive or negative. So we're going towards positive infinity here. So we're going to assume x to be a very large positive number. When we take the cube root of a positive number, we get a positive number. Similarly, when we raise a positive number to the 7th power, it's just 7 positive numbers multiplied, which will always give us a positive number. Therefore, a positive number to the 7/3 power will be another positive number. Therefore, in the numerator, we end up with a positive, and in the denominator for x to the 7/3, we end up with a positive. Therefore, we end up with a positive over a positive, which is just a positive number. Since our analysis of the positives and negative tells us that the limit needs to be positive, since the function is positive as we go towards infinity, we'll take the positive ratio of the coefficients. So the limit as x approaches infinity of f of x, where f of x is the function given, will be the positive cube root of 3/2. For our third example, we want to find the left-sided limit, the right-sided limit, and the two-sided limit of as x approaches 3 of x divided by x minus 3. Since we're asked to find one-sided limits here, the first thing we're going to want to do is actually try to solve the third one and see if we could first find the two-sided limit just by plugging in x equals 3. So to do that, we're going to start off by writing the function and then plug in x equals 3. Doing so gives us 3 divided by 3 minus 3, which equals 3 over 0. So unfortunately here, we see that the two-sided limit gives us an undefined value. Therefore, we can't just go forward and say the two-sided limit is equal to our one-sided limit. And instead, we're going to have to get a better answer than just being undefined. To do that, we're going to want to plot our function. So what we're going to do is we're going to sketch it, and we're going to see what we get around the region as x approaches 3. So let's say here is x equals 3, and what we're going to want to do is we're going to want to plug in something very close to 3 to our function x divided by x minus 3. So if we plugged in 2, for example, we would plug in 2 divided by 2 minus 3. Which would then be 2 divided by -1 or -2, which would be down here. Now if we plug in something even closer, such as 2.9, we would get 2.9 divided by 2.9 minus 3, which would be 2.9 divided by -0.1, which would be -29. So we see that as we get closer to 3, we're going to continue getting more and more negative as our denominator gets closer and closer to 0, but remains negative. Therefore, to the left, we're going to see that our graph looks like this. Now we're going to look at values to the right of x equals 3, starting with x equals 4. This gives us 4 divided by 4 minus 3, or 4 over 1, which just gives us 4. So at x equals 4, we're going to have this point here. Now let's try something even closer to 3, but just slightly larger than it, such as 3.1. That would give us 3.1 divided by 3.1 minus 3, and that would be 3 over 0.1, or 30. So we see that as we get close to x equals 3 over here, or to the right of x equals 3 to be precise, we're going to continually increase in the positive direction. So our graph sketched looks like this. Since you should get used to not having formally plotted graphs and just relying off your sketch, I did not plot this function in Mathematica, but what we have here will still allow us to find our limits. So first we're going to look at the limit as x approaches 3 from the left. To do that, we're going to look at the values less than 3, which is along this line here. We see that the function is continually decreasing without bound. Therefore, the limit as x approaches 3 from the left of x divided by x minus 3 is going to give us negative infinity. Now let's look at the limit from the right. For the limit from the right, we're going to look at the values greater than x equals 3. So we're going to look here. What we see is here, when we come from the right side and approach x equals 3, we're increasing without bound. So we say the limit as x approaches 3 from the right of x divided by x minus 3 is equal to positive infinity. Lastly, we're going to now look at the two-sided limit. Remember, for the two-sided limit to exist, the limit from the left has to equal the limit from the right. Since the limit from the left is negative infinity and the limit from the right is positive infinity, they are not equal. Therefore, our two-sided limit can't exist. So that is our final answer to this last part. So this would be the one-sided, the two-sided, and the left-sided, the right-sided, and the two-sided limit around x equals 3 of this function. For our last example, we're going to look at the limit as x approaches 1 of x to the 4th minus 1 divided by x minus 1. We're going to start off the same way we typically start off a limit problem, and that's we're going to write our function and try to plug in the x value. So we're going to write our function and plug in x equals 1. Doing so gives 1 to the 4th minus 1 divided by 1 minus 1. Unfortunately, though, this gives us 0 divided by 0, which is an indeterminate, meaning we have to do more work to find our final answer. What we're going to want to do when we get an indeterminate is we're going to want to try to simplify the numerator and or the denominator by factoring when we have polynomials or by working with the conjugate when we have radicals. Since we have polynomials here, we're going to want to try to simplify our function when using factoring. So we have x to the 4th minus 1 divided by x minus 1. However, we could simplify this by factoring the numerator. We see that x to the 4th and 1 are perfect squares, and we're taking the difference between them. Therefore, we could factor it using the method of the difference of two perfect squares to get x squared minus 1 and x squared plus 1. And then we still have our x minus 1 in the denominator. Unfortunately, though, we still can't cross anything out, so if we plugged in x equals 1 now, we would still just get an indeterminate. However, we could factor the numerator further because x squared minus 1, the first term, is still the difference of two perfect squares. So we could factor it further to get x minus 1 times x plus 1, still times x squared plus 1, divided by x minus 1. And now we see that our x minus 1's cancel out, and x to the 4th minus 1 divided by x minus 1 is equal to x squared plus 1 times x plus 1, so long as x does not equal 1. And now what we can do is we can now go back and plug in x equals 1 to our new equation. So when we take x squared plus 1 and times x plus 1, and we plug in x equals 1, what we find is we get 1 squared plus 1 times 1 plus 1. And this just gives us 2 times 2, or 4. And that's going to be our final answer for this limit, that the limit as x approaches 1 of f of x is equal to 4. Just to quickly reiterate what I've said in previous videos, the reason why we could say that the limit is 4 even though when we when we evaluate it at x equals 1, we get an indeterminate, is because the limit is unaffected by what the actual value is, and instead it only matters what is being approached, as that is what the limit is. The limit is telling you what value is being approached. With that, that concludes this video. I don't have any additional practice questions here. Thank you so much for watching. Feel free to leave any questions you have in the comments below, and have a great day.